Hi all, welcome to the honors course on machine learning. So this course is uh, computational fundamentals of machine learning. It can be studied by the fourth semester computer science students under KT. Okay, linear algebra is today's topic, and the role of linear algebra in machine learning. Coming to our lectures. Linear algebra. What is linear algebra? Linear algebra deals with linear equations. And what are linear equations? We have seen many kind of equations in our math class. And linear equations are equations which has all the variables in first degree. Okay. All first degree equations are called linear equations. For example, I can write an equation like this: 2x plus 3y is equal to 0. Okay, I can say this is a first degree equation. So how do we find that this is first degree? We'll look at the variables. So the variables are x and y here. Okay, so it is a two variable equation. And check the degree of these variables. So the degree of this variable is 1 and the degree of this variable is also 1. So these in this equation, the variables have the degree 1. So we can call it as a first degree equation. Okay, this is a first degree equation. And if I write something like this, is it a first degree equation? No, because the variables have a higher degree, right? So this is not a linear equation. And if the equation is something like this, still this is not a first degree equation. So one of the variable has a higher degree. So this is also not a linear equation. So we can consider a linear equation like this. Okay, in general form we can write like a11 x1 plus a12 x2 plus etc. a1n xn as equal to b. So this b can be any value, and this a1 a11 a12 a1n etc. are coefficient values. Here it is 2 and here it is 3. Okay, so those are the coefficient values. This is the general form of a linear equation. Okay, and why we study linear equation? Because in machine learning, this linear equations play a very important role. Linear equations can be represented with vectors or with matrices. Okay, so there are two kinds of representations for linear equations. One is vector form and the other form is matrix format. And these are essential to machine learning. So even the vector notations or the matrix notations, both are very essential, very relevant in the context of machine learning. In order to represent the machine learning algorithms or to represent the machine models, we are using linear equations. They are in the form of vectors or in the form of matrices. Okay. So in machine learning, we heavily use vectors and matrices. Let's see some example. So we have a picture of a flower, and we give this image as an input to our machine learning system. Okay, and what the output we are expecting is the machine learning system should check the image and it has to give us an output something like this. Okay, since the petals are white colored, so the machine learning system will give an output like this is a white flower. Okay, so take this simple example and where comes the matrices and vectors. So here I am going to describe the use of matrix. So the very first use of matrix in this particular case is to represent the image itself. Okay, so if we have a figure like this, and how do we input this figure to our machine learning system? That is the very first step. Okay, and the machine learning system can only understand numbers. That is a very basic thing. A machine learning system can understand only numbers. Even if we are inputting some text values, some text or some sentences to the machine learning system, finally that sentences has to be converted into some form of numbers. Then only the machine learning system can understand it. Okay. So here our concern is to convert this image, this white flower image into a number format. So the widely accepted numbering system or representation of the images are in the form of matrices. So flower is represented as matrix data. Each pixel value will be one entry in the matrix, and that means how do we represent the flower in the form of a matrix? So we consider each pixel value of the flower and represent those pixel values as the matrix entries. Okay, so let's have a pictorial representation for the same. So I have taken a random matrix here. It is not actually representing this particular image, but just for the sake of understanding, I have given a matrix like this. Okay. So each number 0 or 1, so basically this matrix represents only black and white images. So when the pixel is value is 0, that represents a black spot, and if the pixel value is 1, that represents a white spot. Okay. Hope all of you are familiar with the pixels. You can divide the image into different simple basic units called pixels. So I can say that a single point on this image as a pixel. So that is the simplest way of explaining pixel. And that dot may have the color white or black, and if it is black, we represent a corresponding 0 over here, and if it is white, we will represent it as a 1. Okay, so this is the very first use of matrix in machine learning in order to represent our data. We call the inputs as our data. Okay, so the data to the machine learning system are always represented in the form of a matrix. Okay, or in the tabular form. The algorithm to classify the object as flower is represented using linear equations. So this can be represented in vector form or matrix form. The linear equations, we can represent it in matrix form or in vector form. And what are vectors? Vectors are objects which have magnitude and direction. This is what we studied in our physics class, in our school days. For example, the very familiar example we have seen in our physics classes is force. Okay, force has some magnitude as well as direction. And we normally represent it like this, with an arrow over the letter F. This arrow always says that this quantity has a direction value also. And the properties of vectors. So vectors are very much important in machine learning. So we should know the properties of vectors. First and very important property of vectors is we can add two vectors. Addition of two vectors are defined. Okay, we can add two vectors. So for example, I have two vectors x1 and x2. I can add these two vectors and this result will give you another vector. So when we add two vectors, we will get another vector. That is the very special property of the vectors. And the second property is we can multiply a vector with a scalar value. Scalar is nothing but some real numbers. It belongs to some real numbers. And I can multiply a vector with a scalar value, and that product will also give another vector. Suppose I have the vector x1 and I multiply it with 2, I will get another matrix, another vector. So the resulting, suppose the resulting vector is x2. Okay, so x2, so the result of this product will be a vector again. So these are the two operations allowed with vectors. We call them as vector addition and scalar multiplication. Or we can say that vector addition and scaling. That is the term we use. Scaling means we can increase the magnitude of the vector or decrease the magnitude of the vector. Okay, so we can stretch the vector or we can reduce the vector. So these are the two operations allowed. And we cannot divide two vectors or we cannot multiply two vectors. Okay, so multiplication and division are not possible with the vectors. Okay, so always keep it in mind that we can add two vectors, we can multiply a vector with a scalar value. Okay. Then different types of vectors. Basically, we consider some of the vectors that we use in the machine learning systems. Okay. So for the clarity, first of all, we are looking at the geometric vectors. Okay, geometric vectors, then polynomials, audio signals, tuples of real numbers. These are the four topics, four kind of vectors we are interested in the context of machine learning systems. Okay. And first one is geometric vectors. They are nothing but directed line segments. Okay. So I can say that this is a vector. And earlier we said that it has a magnitude, the vector has magnitude and direction. Magnitude and direction. And the length of the line represents the magnitude and the very direction represents its direction. Okay. So it is the directed segment. And how we can specify that this directed line segment is a vector. So vectors should satisfy the addition operation addition and scaling. Okay, and let us check how this geometric vectors represents or shows these properties, addition of two geometric vectors, whether they result in another vector, or when we multiply it with a scalar, whether it results in another vector. And let's have an addition. Okay, suppose consider the xy plane. Okay, and we have vectors like this, one vector over here as x1, and we have another vector like this, x2. And how do we find the sum of it? We have to replace this one like this. We have to move this x1 x2 to the tip of x1. Okay, so first take the direction of x1, then take the direction of x2, and this will give you the result of x1 plus x2. Okay, so this inclination, this direction, and the length should be exactly same as that of x2. Okay, then you will get the sum of, and this resulting vector is the sum. Okay, so using x2 and x1, I am representing another vector called x1 plus x2. Let it be as x3. Okay, so I can say that x3 is the sum of x1 plus x2. So addition is possible here. When I add two geometric vectors, I will get another geometric vector. So addition is satisfied here. Now let's check the scaling operation. So we have the xy plane, and I have two vectors, one vector I have here called x1, and when I multiply this x1 with the 2, suppose I want to multiply it with 2, when scalar multiplication is done, what happens is the length of the vector increases. The length of, or the magnitude of the vector is multiplied by 2. So internally this line of the length will be doubled. So the new vector will be like this. So it has the double length of x1. So the full length is called, so this entire one represents 2x1. Okay, so we can see that it is finally end up in another vector. Okay, let it be x3. Okay, so this longest one is called x3 vector, and x3 is actually multiplication of the vector x1 with the scalar value 2. Okay, so geometric vectors satisfies these two properties, that is vector addition and the scaling. Now polynomials. Again, polynomials, we have to check these two properties, addition and scaling. Okay, so we have to find out when I add two polynomials, whether the result is also a polynomial. So let's write some polynomials over here. So I write 2x plus 3y plus x is z. Okay, then another polynomial. So these are multivariable polynomials. 4x plus 8y plus 5z. Okay, so if I add these polynomials, what we get? These are 6x plus 11y plus 6z. Okay, this is also a polynomial. Okay, so this is addition property satisfied. Now I am going to multiply the first polynomial. So this is the polynomial 1 and this is polynomial 2, and I want to multiply p1 into 2. What happens? 2x plus 3y plus z into 2. What happens? It will give you 4x plus 6y plus 2z. It remains a polynomial. So the scaling operation is also satisfied. So we can say polynomial is a vector. Okay, we can consider polynomials as vectors. Then the audio signals. We can consider audio signals as vectors. Why we are interested in audio signals means in some machine learning systems the input may be audio signals. So we are using audio typing systems in our WhatsApp or in Google. What we are doing is we are giving audio signals to the system and it is converted into text. Okay, so our machine learning system may be and they may need to handle audio signals. Okay, so in that context we are considering audio signals also. And the interesting thing is audio signals are also vectors. We can consider audio signals as vectors. That means they have these two properties, addition and scaling. Okay. And when we add two vectors, what happens when we add two audio signals? So assume this is first input signal and this is the second input signal. And when we add these two signals, we get the output as another audio signal. So the addition is satisfied. And what about scaling? We are very much familiar with amplification of signals. So in amplification, we are actually scaling the audio signals. So the two properties satisfied. Okay. So we can see audio signals as vectors. Then tuples of real numbers are also being considered as vectors, because when we add two tuples of real numbers, we will get another real number. Okay, so I consider the tuples. We can consider the represent the tuples like this. Rn means it's a vector with n numbers. Okay, n numbers. It's not. It is not ordered. It can be any real numbers over here, but there will be n elements. If I represent R2 means it's a two numbered vector. Okay. Then R3 is three numbered vector. Okay. So when we add two vectors, suppose I have a vector called x1 and x2. They are belonging to R2. When I add these two vectors, x1 plus x2, that will also belong to R2. So let's take one example. So 1x1 is equal to 3, 0 and x2 is equal to 4, 5. And if I add these two vectors, x1 plus x2 will give you another R2 vector. So this also belongs to R2. So addition is satisfied. And if I multiply this x1 with a scalar value 3, what will be the output? The output will be 9, 0. So this also belongs to R2. So the addition as well as scaling are satisfied in the case of tuple of real numbers. So I can say this is a vector. So tuple of real numbers as vectors. So that is all about the basics of the linear algebra. Thank you.